Good afternoon, everyone. Thanks for the organizer giving me the to give me the chance to presentation my work. I'm Lijiong from Quantum Optics Group in National University of Singapore Center for Quantum Technologies, this work also collaboration with various theory group in CQT and other research group over the world. So if we look at the title, the first keyword is randomness. Randomness is a very important concept in our modern life. And here is an example. We generate randomness from a classical system with a program called Random in 1960s. It looks quite random, but if you change your viewpoint, you can see there are some correlation between points. So this is not suitable for like cryptography or simulation applications. Actually, the classical word is a deterministic word. So any random number generated by classical word is not a true randomness. However, the quantum mechanics is a probabilistic theory. And take the first, simplest example, a photon going to a beam splitter, transmitted or reflected is purely random. But such kind of random number generator have a problem is you need to trust the device, or you say you need to believe no one is hacking the system. So the idea of this project is we want to generate a certified randomness from the Bell test. And this is a simple diagram for the Bell test with photon system. We have photon pair source, emit out 2 photons to Alice and Bob. Both of them have a halfway plane and PBS to change their measurement basis. And they have 2 detectors to measure their photons. So for Alice and Bob, they have 2 measurement bases. And 2 times 2 overall have 4 measurement bases. So for each measurement basis, the possibility of the 2 photons arrive at the same detector, both are plus or minus, minus the possibility of the photons arrive at different detector, giving me the E value. By combination of the 4 measurement bases, you can construct the S value. So if the S value is more than 2, we say we violated by inequality, and the system is non-classical, and we can generate a true randomness from the system. Because classically, the S value can never be more than 2. Then here is just a simple diagram. I want to show you if the S value is less than 2, there is no randomness at all. And if the S value is more than 2, the higher the number is, the more randomness you can extract per measurement round. And this is simply based on the entropy calculation. So since 1964, the Bell test will be pointed out. There are lots of Bell tests have been done. And most of them have loopholes. One of the famous loopholes is called detection loophole. If we take the photon example, the function of photon you measure should be large enough to well represent your samples. Otherwise, there is a loophole. And the theoretical threshold is more than 2/3. So since 2010, people start to extract randomness based on the Bell test. And the first experiment closed the detection loophole and generated about 10 power -5 random numbers per second, which is not so high for any application, but it's proof of principle. And this is used the atom system because the low repetition rates. So later, people start use photon system, and we can see last year the Lijiong, their research they published, they can extract more than 100 bits per second. With that system, and recently they have a new paper, they can extract 180 random bits per second. And besides the detection loophole, there are also other loopholes. So the orange dot is experiment close the 3 main loopholes and extract randomness. So just now I showed you the diagram is with 4 detectors. But actually, if you think if your detector is high efficiency, actually, you don't need the 4 detectors, because if the photon is not to be measured at the transmitted detector, it will be reflected. And here, we also use the continuous wave source, CW source. So one further of the source is you don't know when the photon will come. So the measurement data will be looked at like this. At the Alice and Bob side, both of them recorded down the time arrival of the photon information, and then we have the timeline there. So the problem for the continuous wave source is it's quite hard to definition a measurement round if we compare with the power source. So here we use the time binding method, which means we recognize the measurement events into a uniform time bin tau. So within the bin tau, if there is a photon, we label with plus. There is no photon, we label with minus. And there is multiple photon, we still label with plus. So with this labeling, we can construct the E-value and construct the S-value for the bias inequality. So this is some real experiment data for Alias and Bob. I want to show you, first I bin it with tau equal to 13 microsecond, and I get the E-value equal to 2/3. And if I slightly change the tau to 20 microsecond, the E-value become negative. So later the S-value will be largely depend on the binning with tau. After all the introduction, let's now look at the experiment setup. Here we generate the entanglement by a Sonic interferometer by type 2 SPDC process. Basically, we put a PPKTB crystal, periodic Pauling KTB crystal, inside the waist of a Sonic interferometer, which was labeled with the radio triangle, and then we pump it from both sides. So in each pump side, you can generate photon pairs, and the A10 light generated for the both sides will be overlapped at the center PBS and generate entanglement state phi equal to cosine theta HV minus EI phi inside theta VH. The angle theta is controlled by the relative pumping power of the blue, so which was provided by a continuous wave 405 nanometer laser, and the relative power is controlled by a halfway plate and a PBS. And the relative phase phi is controlled also by the relative phase between the two pumps. So we put a thin glass inside one pump arm to control the relative phase phi. By carefully adjust the pumping beam width and the collection width, we can couple around 90% of photon from the source into the single mode fiber for 810 nanometer. But in order to close the detection loophole, we also need to have a high efficiency photon detector. Here we use the superconducting transition edge sensor, which is a superconducting material put at the transition edge temperature around 18 millikelvin. So that detector the resistance of the detector is very sensitive to the environmental temperature. So when a photon arrives, it will heat up the detector and change the resistance. We measure it by a biosystem, then we detect the photon. So the advantage of this detector is it has a very high quantum efficiency, more than 98%, but the jitter is around 170 nanosecond. So this is efficiency measurement on our system. We pump the crystal with about 5 milliwatt, 4-5 nanometer continuous wave laser beam, and we generate about 24 kilo photon pairs per second. And for both Alice and Bob, we measure more than 82% efficiency, which is rarely above the threshold of 2/3. And we also get relative low dark count, slightly about 40 for each detectors. In 1993, Eberhard published a paper claim if we use the non-maximum entangled state, we can close the detection loophole with more than 2/3 efficiency. If we use the maximum entangled state, the requirement will be more than 80%. So here is the optimal state for our system to close the detection loophole, and I label it with the dashed circle. And this is the state measurement on our system. We can see it's feel quite well. Actually, the fidelity is more than 99%. And for the non-maximum entangled state, the measurement base is also a bit different from the normal measurement base for the Bell test. And I label it with the solid line against the normal basis with the dashed line. So now we can look at the result. So the vertical axis is S-2. So it means if it's more than 0, we have a relative Bell inequality. And the horizontal axis is the binning width. And we can see there are two curves. The orange curve is the simulation based on our system's efficiency, dark count, and so on. And the blue dots is the simulation, is the real experiment data. They fit quite well. There is a slight gap between them. That's because the state fidelity is not really 100%. And then we get to the highest violation around 30.15 microsecond beam width, and the S value is about 2.016, which is kind of highest for a photon system without detection loophole Bell test. And then we can also see at the corner, which is close to the 0 microsecond beam width, it not violate the bioinequality anymore. That's because our detector have about 200 nanosecond jitter. So when the binding size is too small, the jitter will misleading the photon into a wrong beam, making it not a violation of bioinequality anymore. And after the violation, now we can talk about the rate of randomness. This is two figure, beats per round versus spinning tau times rounds per second versus spinning tau. So by time this, we get the how many beats you can extract per second versus the beam width. Again, the orange line is the simulation based on a system. We can see the small beam width is the more randomness you can extract. That's because although the randomness per measurement round is smaller, but you get a much more rounds when the binding width is small. And for the real experiment, it starts to drop down at a certain point. That's again because the jitter time of the detector. And at some certain point, you cannot extract any randomness at all. And this analysis is purely based on the entropy. And in real time, so it means you need to do an infinite time measurement. But in the real life, we don't have infinite time, so we use the finite statistics. And here we use the traversal extractor. The basic idea is you have n measurement rounds, and you apply the extractor, you set some security parameter because of the finite size, and you get m random bits. Here we set the image sequence S equal to image sequence C equal to 10 power minus 10. That means after extraction, the random bits is uniformed within 10 power minus 10. And the traversal extractor we are using compared with the normal extractor people are using, like topless extractor, we don't need to import too much randomness. And also it's secure against the quantum adversary. So in a 26 minutes measurement, we generate more than 600K random bits, which correspond to close 400 bits per second. And the left side is how many measurement rounds we have, and the right side is how many random bits we extracted. Now you may ask, why not you measure longer and get more random bits? Yes, we do, but there is one problem. So the processing time for the 26 means data is about 9 hours use a normal computer server. And I represent the time with the red dot there. However, we also do more than 10-hour measurement, but the processing time is around 28 years. I represent it with the blue cube. 28 years may be too long for my PhD. So if we change to the turbulence extractor, we can extract more than 900 bits in hours. So this is our point of the state of arts. Our experiment generated about 400 random bits with a short measurement with a traversal extractor, and for a long measurement, we can generate close to 1,000 bits per second. In conclusion, we violate the Bayer inequality without detection loophole, and we get the S value equal to 2.016. By the binning method, we can flexibly adjust the measurement round, and we can get the asymptotic value of random bits about 1.3K bits per second. So this is our research group. This work is mainly with my research partner Jian, my postdoc Alessandro, and my boss Christian. There is one more advertisement. Although I'm working in Singapore, but I'm a Chinese. So I'm from Suzhou, which is a very beautiful city, and just like a half-hour train away from here. So if you have a time, you can go there, take a visit. It's a nice place. Okay, thanks.
Thank you very much. We have time for questions.
So you didn't consider about the locality loophole problem, right?
Yeah, in this experiment, we haven't closed the locality loophole.
Yeah, I mean, if you talk about the device independent, there may be some problem, that because the two detector, if you purchase the two detector from outside and if they can communicate, then
for the continuous wave case, actually, we also think about doing a loophole-free bell test. Mm-hmm. But if we want to do a loophole-free bell test, we need to have a very fast detector because the TS is too slow. And
I don't know. The Anton Zeilinger published a paper with the TS with the loophole-free.
Yes, but if in the pulse case, I think it's okay. But if in the continuous case, it's have some problem.
Yeah, I mean, if you want to distribute it to some distance, and then the efficiency of your setup will reduce, and then the
Yes,
bill
yeah,
rate
that's
probably will
also
reduce.
another problem. But for now, we are actually about 82%. And so for a fiber kilometer, it's maybe reduced like 2 or 3%. And actually, we can further improve it because here we use a free space link between the detector and the source.
Okay.
Actually, there the transmission is about 95%. And also for the detector, we are not really, because for TS, it intrinsically don't have any daytime.
That's
But
right.
during the measurement, actually, we just set some threshold. So we artificially introduce some daytime to reduce like 1 or 2% efficiency, something like that.
Okay.
Other questions?
So for your time bin implementation, you have a lot of empty time bin not used, right? So in your detection, you divide it's a CW. So a lot of time bin
Yes,
is
there is
empty,
no-
right?
yeah, yeah.
So I'm wondering, can you apply and can you use this empty time bin to have like a high dimensional DI QRNG implementation? Is it possible? Then your rate will be much higher.
To be honest, I haven't think about the high dimensional program. But I think ideally it's the same as the pulse case. You just adjust the average photon number per bin. Like it's similar to average photon number per pulse. And so here the binning is just adjust the average photon number per pulse. The advantage is you get much more bins and you push up the random bits. And we can further push up random bits just like a pump hard, smaller bin width, and like get a faster detector or something like this.
Other question? I have a last question. You mentioned the rate of the randomness highly depends on the bin width selection.
Yes.
But do you consider the contribution from the experimental devices such as the transition edge sensor detector? Because this detector have a very large time resolution.
Yeah, it's have a quite large jitter. So when the bin width is small, the large jitter will make you not violate binding quality anymore, or make your violation very small. So the random bits will start reduce down, which was in the red dots. Yeah. So the main limitation make it not fit very well at the small bin size is just because the detector is slow. Yeah.
Okay, thank you very much.
Thanks.
If no question, let's thank the speaker again.